we are looking at this new carbon family, and in yesterday's lecture I specifically covered on the various aspects of this new carbons which are identified, the discoveries that underlies this new allotropic forms, and also specifically we discussed about the chemistry of fullerenes. In today's topic I would like to focus little bit more on the carbon nanotubes because of its application, and then we will also look into the issues related to graphene, the discovery and the properties related to graphene. So, just as a quick recap of what we saw yesterday on carbon nanotubes, we said carbon nanotubes are those which are confined in one dimension, and the way we roll these graphene sheets in different vectors determines whether we get a zigzag carbon nanotube or a chiral or a armchair type, and depending on the way it is scrolled, it also alters the electronic property, and therefore you can look for a metal or a semi metal or a semiconductor. And the chiral vectors are also the ones which decide the angle with respect to the CH vector, and therefore we can get different forms of carbon nanotubes. And we also looked at another view graph where we said there are three basic ways of preparing. One is CVD technique, another one is the arc discharge, and also we have another technique using lasers. So, there are variety of ways that we can release this carbon nanotubes, and one of the controlled way of growing these carbon nanotubes is to grow in one dimension as pillars. So, how do we do that? Take methane and put that on porous silicon, and porous silicon is actually capped with the iron as nucleating centers. So, the carbon nanotube will actually get will keep growing on the iron clusters. As you see here, these are the iron regions, iron patterns, and these iron patterns will help the carbon nanotubes to grow in this fashion. And what we see here in this view graph is the oriented crystal growth. So, if you can actually pattern your porous silicon in this way as you see from the top, then you can find out or you can realize such nanostructures growing in a preferred oriented form. So, these are patterned way of growing silicon nanofibers. So, you do not necessarily need to get a bundle, but it can be streamlined, the growth can be streamlined, and therefore, the growth process is actually a base growth mode, which means it will only nucleate on a particular metal where it is catalytically getting decomposed and it grows, and if you pattern the base, then accordingly the growth of the carbon nanotube also proceeds. If you do not pattern, then you get a bunch or like a forest, it grows in one direction. So, the growth mechanisms are very important to understand the electronic and mechanical properties, because both are dependent on the atomic structure of the tube. What we need to understand is that what are the parameters that control the size, number of shells if it is multi-wall, and the helicity and structure during the synthesis. What has been proved and established is that there is no way you can grow a carbon nanotube without a metal catalyst. Therefore, that is much important for the synthesis of nanotubes, and the size dependency comes with the nature of catalyst and the growth temperature, etc. Now, regarding the mechanism of single wall growth or multi wall, there are different models that are proposed to understand, because this happens in a very transient way. Therefore, one does not really know what is the mode by which multi-walls propagate or single walls propagate, but there is some fair idea about how the whole thing happens. Open ended growth of multi-wall nanotubes seems to occur mainly because of the role of hexagons and pentagons, which play the important role in propagating this along one axis. As you see here, these are C2 clusters, these are C3 clusters, and the way they go and join to the nanotube which is growing determines whether it will be open ended or whether it will close, or whether what will be the length scale of the growth process. So, typically this sort of units do help in realizing whether there will be a closing, because this can be, both sides can be open ended also when it is growing along a preferred axis, but in most of the cases we see that the carbon nanotubes do close in one end to attain stability. And why it happens? Mainly because of the role of this hexagons and pentagons and the way the carbon clusters keep on getting accumulated. When we come to multi-wall nanotubes, the possibilities are immense, and therefore there are very few ways that you can map to understand. As you see here, this is a single wall, and as the carbon supply is coming, the second wall can actually grow as an open ended wall, or this can close and the third wall can propagate. So, the way the multi walls evolve depends mostly on the way the carbon supply is, and also it depends on the way the growth direction is. So, this is a contour which tells what are the different ways this multi-wall structure is happening. As you see here, this can unfoil like this and again go for the third growth, or this can actually go to close the second layer, and so on. So, there are different combinations which are worked out, but as far as the multi-wall nanotube growth is concerned, two parameters are important. One is the way the carbon supply is and the growth direction that proceeds during the growth. So, both are important, whereas for single wall growth mechanism, it has also been tried theoretically through simulations to find out if uncatalyzed growth is possible for single wall, and what has been found out is that such uncatalyzed reactions are possible only at temperatures of 2000 K to 3000 K. Therefore, for single wall nanotube definitely there is a much clearer mechanism than the multi-wall, and what is implied here in the study is that the nucleation through the metal center is very important for single wall nanotubes, and the closure of these single wall nanotubes actually reduces the reactivity, in other words makes the tube stronger. Therefore, the closing also occurs. And how does this happen? Actually, if we take a fluorine molecule and then the fluorine actually has these nucleation sites of the metal, of these metals lying in this direction, then you can see the single wall nanotube is actually propagating through these links. So, this is one of the way that we can visualize how a single wall can come compared to multi-wall. So, transition metal surface decorated fullerene, they nucleate the growth around the periphery, and what is the role of the catalyst there? Catalyst keeps on coming out along with the growth. So, this sort of catalyst atoms do stick to the edges of the carbon nanotube. So, catalyst atom chemisorbed onto the open edge, and this keeps the tube from scooting around the open edge. This will ensure that pentagons and heptagons do not form. That is one of the reason why a long chain single wall nanotube is possible with this sort of mechanism. And if you really look at the way this field has grown with this basic understanding of how to make a single wall nanotube or a multi wall nanotube, sky is the limit, because the way people have mapped different derivatized single wall nanotubes or taking it through some functional applications, there has been a skyrocketing effort. And you can see here some of these view graphs just to highlight what all can happen. Here this has been used for electrical applications, and you can also spread this carbon nanotube like a screen, to go for large area deposition. And as you see, you can even roll it to 6 feet on a paper or plastic substrate. So, processing of this carbon nanotubes to larger areas is possible, and here in this cartoon you can find that the carbon nanotubes in the edges can be functionalized. When we say functionalize, you actually oxidize it and convert it into COOH, the terminal carbons, and then you try to attach it to any material. As you can see here, you can almost simulate the sugar units here, and CG80 pairs can be paired up, which is also seen very clearly from the AFM pictures. So, when you substitute this carbon nanotube, then they show a contrast here. These are the carbon nanotubes that you see in the AFM picture, and those which are highlighted here are the substituted ones. So, it is possible to go for a variety of substitutions on this single wall nanotube, and if you want to make extensive substitutions, then not just one, you can try to oxidize it. The more you oxidize it, the more you generate COOH groups in the terminal positions, and then you can actually attach a variety of molecules to it. The research has now reached to the extent where you can actually do it in lab scale in a very defined way. So, this is one of the setup where you can realize single wall nanotube preparation even on a lab scale. And the best part of carbon nanotube, as I mentioned in the earlier slide, is the enrichment of this metallic carbon nanotubes, and we can also not only enrich them, but we can go for preferential oxidation of this nanotubes to a larger extent. So, as you would see from this picture, that with more and more of selective oxidation, the color of this nanotube solution changes. So, these are those which are oxidized, which means more and more of COOH groups are attached to the terminal carbon. So, we can try to enrich that, but the best way to characterize if you are able to really functionalize these carbon nanotubes or whether they remain as pure nanotubes, Raman spectra is one of the best way to analyze. And here are 4 important reflections that we should bear in mind, which gives us a clue how to map the purity of it. The first one is your G mode, which is the very important mode, which is G from graphite. This mode corresponds to planar vibration of carbon atoms and is present in most graphite like materials. So, this G band in your single wall nanotube is shifted to lower frequencies relative to graphite and is split into several peaks. So, this is the peak that you can map, and if there are several splittings in this, as you can open this peak, you would see several splittings. Splittings really give the clue that these are single wall nanotubes, whereas the graphite will actually give a very intense single line. So, this is one way to map the formation of single wall nanotube. Another one is the radial breathing mode, which corresponds to the radial expansion contraction of the nanotube. Therefore, the frequency depends on the nanotube diameter and can be estimated. As I told in the previous lecture, that we can actually alter the diameter of these nanotubes. So, this radial breathing mode is one measure by which you can analyze the diameter. So, if you because this is very sensitive, and with the diameter of the tube this radial mode would shift. So, you can estimate whether you have a preferred dimension or not. And another important mode is D mode, is present in all graphite like carbons and originates from structural defects. So, this is one important feature which will give us clue whether you have functionalized your carbon nanotube, and this D prime is also called D prime. This G prime is nothing but your second overtone of D, and the intensity of this will tell whether you have functionalized the single wall nanotube or not. For example, if you are treating this with nitric acid and then boiling it, then this peak would actually be a measure whether you have functionalized your nanotube or not. If this is really absent, then you say that it is a single wall nanotube. So, this is not only a measure of the defect structure in your carbon nanotube, but this also tells whether you have functionalized it. So, this serves as a very good optimization for your single wall nanotubes. And when we come to the optical properties of single wall nanotubes, you would see a typical absorption peak for carbon nanotubes, where beyond the 3 electron volt this is due to plasma absorption, whereas there are peculiar reflections due to S11, S22, M11. This S11 or S22 is actually to differentiate between metallic or semi-metal carbon nanotubes. In semi-metal zigzag nanotubes, metallic, this will be more prominent, S22. It can be called as E22 if we do not know the metallicity, or for the semi-metals or semiconducting nanotubes, this is S11 reflection. So, these are two absorption peaks which really play a very important role in mapping, and here again we see the profile of the excitation wavelength versus PL wavelength. As you would see here, these are plotted against the unit vectors m and n. So, whatever numbers that you see here shows that for M0 repeats, you do not see any photoluminescence, neither for m is equal to n. Okay. So, the values in the parenthesis clearly tells us what sort of mapping or what sort of orientation of the nanotubes which are going to be effective for photoluminescence. But the good news is that carbon nanotubes show a very strong photoluminescence, but it is also dependent on the chirality. So, depending on that we can map the photoluminescence response. As I told you, this E11 or S11 is dependent on the metallic nanotube, and this is for the semiconducting nanotube. So, if it is semiconducting, then we mention this as S22 specifically, and if it is metallic it is S11, and this S11 and which is nothing but E11 in this diagram is a transition from V1 to C1. So, when electron is getting excited to C1, then a electron hole pair is actually formed, which by a phonon assisted process relaxes, and then the emission comes out to be a C1 to V1 emission. This is what is responsible in the case of metallic nanotubes, and this is also called as first Van Hove optical transition, which talks about the transition that is responsible for the absorption. And in the case of semiconducting single wall nanotubes, you would see that the density of states are slightly different from the metallic nanotubes. these are much more discretized, and this sort of density of states what you see here is nothing but the influence of your one dimensional structure. In one dimensional you would not see a continuous density of states. So, in a three dimensional material for a 3D, the density of states actually would correspond like this, but for a one dimensional nanotube these are all discretized, and therefore you see this sort of pattern, and between the metallic and the semiconducting you can clearly see that the density of states differ very differently, and these are the optical transitions which are responsible for photoluminescence, and in the case of semiconducting nanotubes it is C2 to V2 transitions which are responsible. So, excitation of photoluminescence, an electron in the nanotube absorbs via a S2 transition as I mentioned earlier, and the electron and the hole rapidly relax from C2 to C1 or and from V2 to V1, and therefore the C1 V1 transition is actually responsible for the light emission. And one thing that we need to understand here is the photoluminescence is not due to excitonic emission. This is quite different from the other PL situation, where PL emission usually is a excitonic influence, but carbon nanotube photoluminescence is not a excitonic luminescence, and this because it cannot be produced in metallic tubes, the electron can be excited, thus resulting in optical absorption. But in the case of carbon nanotube the hole is immediately filled by another electron because the electrons do keep coming, and therefore no exciton is actually produced, which is responsible for photoluminescence. This is another thing that we should bear in mind. So, critically if you look at the photoluminescence behavior, the S22 transition and S11 transitions which are for the metallic and semiconducting are also dependent on the tube diameter. So, depending on the tube diameter you can see the absorption will absorption or the energy gap will vary, and for let us take the case of S11 that is for metallic single wall nanotubes. If the tube diameter is less than 1 nanometer, then the band gap is much higher, and the band gap becomes much lower when the tube diameter increases. So, this is one thing that we should bear in mind, and also another important thing that we should find we should see is a crossover transition from C1 to V1 and C2 to V1 is also possible, although they are dipole forbidden transitions. So, all this do influence the photoluminescence, and based on this several applications have been tampered. One is the use of carbon nanotubes as a glucose sensor. Because carbon nanotubes glow, you can use this for mapping certain molecules or for mapping some study. The best part is it is excited in near IR range of the electromagnetic spectrum, therefore it is safer to the cells, and this is the another point is the glow that comes out is different from the other dyes, therefore it is very selective, and continuous fluorescence also does not bleach the carbon nanotube, therefore continuous radiation is also possible, and it is ideal for sensor applications in the body. And what you see here is a glucose monitor. If you have a glucose sensors capped with the carbon nanotube, then you see the mapping can be or the glow can be much intense and rich, and more the glucose present in the blood, then you will see a very high luminescence. So, that could be used as a mapping, and this is the typical emission spectra of your carbon nanotube. If you excite it at 770, then the emission actually comes at 1300 nanometers. So, this is a typical spectrum for carbon nanotubes. Also there are range of applications for carbon nanotube already realized in the market and in the industry. This is a cartoon which tells that it is having a very vivid antibacterial effect, and you can see here the influence of the carbon nanotube compared to uncoated or a region without carbon nanotube. Clearly you can see that the bacterial presence can be removed using the presence of carbon nanotube, and this is also acting as a very good filter because of its very high surface area. And as you would see here, this is a filter that is currently employed in the US Army. Almost everyone is provided with a backpack where this sort of filters are being carried by the soldiers for getting pure water. So, this has a lot of advantage in filtering biological impurities, and in the sports arena people have also used this to improve the strength. It is used in tennis racket, it is used in baseball stuff, and also there are other selective applications where in AFM tip carbon nanotube coated AFM tips have been produced. So, this is one of a very prime application which is being currently exploited, and also this is being used in composite materials. As you would know, you have a matrix which is polymer, and then you try to reinforce with some fillers like fiberglass or Kevlar, but carbon nanotubes added to this matrix seems to enlarge the toughness and the strength of the material to a larger extent. One other application that we can see here is in the use of displays. This is a map of your cathode ray tube, where you know that the electron guns impinge on the phosphors and then you get a full color spectrum, but you can get much sharper contrast and color purity if you are going to use carbon nanotubes in field emission process, because in field emission compared to the cathode ray operation, you see here it is a blend of 3 electron guns mixing the colors, whereas in field emission displays the important point is behind each of the pixel there is electron that is generated. So, it brings color purity and sharpness to a greater extent, and carbon nanotubes are able to improve on this contrast, and it is also used in nanoelectronics now. Carbon nanotubes can be used. So, there are several applications which are being realized for carbon nanotubes. I cannot go on showing more view graphs on the applications, but just to highlight the interest that carbon nanotubes have generated compared to most of the composites that are currently being used. You can see the way carbon nanotubes have taken over is phenomenal, and especially in the last 10 years there has been marked changes happening, and although these are some of the fiber composites which are still being used, but carbon nanotubes have certainly generated a range of interest for applications. Next, I would like to go to graphenes. Graphenes, as I mentioned in the previous lecture, graphene is in 2-dimensional form, and this is also by and large agreed as a material for all seasons. As I told you, if we can really map how the 3D and 1D and 0-dimensional carbons are evolving, we found out in the previous lecture that graphene can act as the base material from which the folding can happen to realize either a buckyball or a single wall nanotube. So, just to highlight the importance, it was these two gentlemen who really did a pioneering work in getting graphene into prominence, and this is again a serendipity because they gambled with the unusual ideas. So, these two gentlemen, both of them are Russians by birth, but they both serve as professors in University of Manchester, Professor Andrew Graham and Professor Novoselov, and both of them tried a very unusual way of getting this graphenes to picture, and this is what we would see for the next few slides. What is this graphene? The graphene, as we pointed out, this is a 2-dimensional hexagonal lattice from where we can either achieve this, or we can actually get these layers of graphene, and this is the basis for C60, for nanotubes and for graphite, and among strongest bond in nature. If you really map this 2-dimensional crystal, you would find that the melting temperature of thin films decreases rapidly with temperature, and therefore monolayers generally are unstable, but in 2004 experimental discovery of graphene shows high quality 2D crystals, and this seems to be coming possibly because of the 3D rippling which stabilizes the crystal. And if you actually find out the representation of this graphene can even extend to 800 nanometers long. So, you can make long stretches of graphene, and the main reason why it stabilizes is because of the 3D rippling which stabilizes a 2-dimensional platform. How to make this graphene, and this is how the discovery of graphene emerged. Strangely cheap and easy. We can draw with a piece of graphite or repeatedly peel it off with a scotch tape, and that is the first experiment that was conducted by these two gentlemen. They just used scotch tape, put it on graphite and keep on peeling it, and what comes out is nothing but a 2-dimensional graphite, and it was almost thought graphite cannot be broken up to such a measure, and growing a 2-dimensional carbon was impossible, but this turned out to be the most simplest way they could engineer. So, place samples on specific thickness on silicon wafer, the wrong thicknesses of silicon leaves graphene invisible, and graphene visible through feeble interference effect. Different thicknesses are of different colors. So, we can easily map from SEM what is the thickness of the graphene layer that you have. Now, we can map it using optical microscope for a quick analysis. SEM and AFM can give you a proper idea. As you can see here, optical microscope image of a resulting flake, which you can take from a sticky tape and then put it on graphite, then whatever you peel it would actually come out like a thick residue which is sticking to the tape, and then you can actually put it back into a mica sheet or glass sheet, which will give you a thin film of graphene. So, we can actually use this graphene as metallic contact in case if we want to study any electrical studies of some other metal. So, the graphene films are actually visualized by atomic force microscope, and this is the way it has been done, and as you could see here, the thickness of this graphene can be mapped using AFM, and this is the TM study which clearly shows patches of graphene here, and here is the SEM micrograph of graphene which shows all the crystal phases of this film that is present. So, it is possible to easily calibrate the thickness of graphene. Just one more mention of how we can make this graphenes. Low cost synthesis of large scale graphenes can be attempted using chemical vapor deposition, and metal layers like nickel, cobalt, platinum, ruthenium is another alternative technique that can be employed. Metal films, example nickel on silicon dioxide is exposed to a flow of hydrocarbon gas, usually it is methane, at high temperatures, causing the carbon saturation of the metal. This is followed by rapid cooling. This is the trick we need to adopt, not just heating, but once you do a rapid cooling here of the sample, then there is a decrease in the solubility of carbon in nickel, which will come out as a graphene sheet. So, it is actually a precipitation process of carbon in the form of ultra thin graphitic sheets, which is nothing but your graphene layers. So, this is the way to realize using chemical vapor deposition. Graphene is actually a single layer of graphite, as we have seen, and the carbon bond in graphene is typically of this order, and it is sp2 hybridized. Actually, if you see, we have partially filled pz or p pi orbitals, which are perpendicular to the plane of the lattice, and these are responsible for providing electrons for conduction. So, it is more like a benzene ring, where your pi orbitals are perpendicular to the plane and your sigma orbitals stabilize the bonding, and therefore, due to this out of plane orbitals, interaction between graphene layers and supporting substrates or between different layers also influence the electronic properties. So, this is the way we can try to engineer. The pi orbitals are the ones which are responsible for any interaction with the substrate. So, this gives also a very good glue or adhesive property for the graphene to stick to a particular substrate. When we look at the Fermi surface of these graphenes, this gives another different dimension to the understanding of electronic properties, because this is a 2-dimensional graphene. Therefore, the way the electronic property is defined in graphene is completely different from that of a 3D metal, and as you would see the Fermi surface of graphene, the plot of Ek versus K, which is nothing but your wave numbers, gives us a different contour for your Brillouin zone. What you see here is the Fermi surface here, which is denoted by this black circle, and against a conventional system which is confined in 2D dimension, here we see that there are 6 double cones, and this is a hexagonal Brillouin zone which is mapped, and this is your conduction band and this is your valence band, and they are actually separated by these 6 points. Okay. And because of this there is a linear behavior between the E and K parameter, and therefore, both the electrons and holes at this point will have a 0 effective mass, and therefore, these points are actually called as Dirac points because they behave like Dirac fermions having a spin of half. And if you look at the typical 2D surface of a material which is confined in 2-dimensional space, this is how it should look like, but for graphene you have a very different Brillouin zone that accounts for the conductivity of this graphene sheets. So, if you take the metallic directions and you try to map it, these are the 6 metallic directions in which the electrical conductivity is confined, and in case of semiconductor carbon nanotubes or the graphene sheets, you would see a opening of this band gap coming between the Fermi surface, across the Fermi surface between the valence and the conduction band. And typically if you map your resistivity as a function of gate voltage, you would see a very different picture compared to the other metals. So, if you make a plot of resistance as a function of gate voltage, you would see this is mostly a ampipolar dependence that is observed for the gate voltage, because you can see the shift here towards one direction, and this is for varying temperatures from 5K to 300K. You can see that there is a very clear response for this graphene sheets against the gate voltage, and also the plot of this conductivity as a function of gate voltage shows this ampipolar property, and the Hall measurement also gives the same feature as that of the resistance. On the right side map you have the picture of AFM picture, which talks about the thickness that we can achieve in such samples. The lighter region what you see here is nothing but the thinnest pass, which is roughly of 0.5 nanometer, and as you go towards the substrate you can see that it is varying from 0.5 to 2 nanometer. When we consider the strength of graphene, it is much more interesting to observe that the graphene can be more stronger than even steel, the strongest steel, because the strength is measured to be 42 Newton per meter, and if you actually take 1 meter square of steel and try to calculate the breaking strength, it will only amount to 0.084 Newton per meter. Therefore, between graphene sheet and the steel there is a tremendous increase in the mechanical strength. So, if you are actually going to spread 1 meter square of hammock like this, this is your hammock, and if you are going to spread for 1 meter square, actually graphene sheet can take load up to 4 kgs, like putting a cat inside this hammock. So, that much of strength can be derived out of graphenes, and therefore it can be used for many mechanical applications. In terms of optical transparency, it absorbs only 2.3% of light intensity. Therefore, a thinner graphene sheet, say 1 or 2 layers of graphene, almost will give you 90% transmittance. So, it can be used as a transparent electrode also. The electrical resistivity of graphene is given by this form, sigma is equal to E N U. If your charge carrier density, which is unusually large, which we can measure from Hall resistance, your N is of the order of 10 power 12 centimeter square, and the mu, that is your mobility, is very huge. So, if you compare that and try to calculate your resistance comes to be around 31 ohms, and for a hammock measuring 1 meter square that we showed, the resistance will typically be of 31 ohm, which is very less. And therefore, if you make a comparison between graphene and other semiconductors like silicon or germanium or gallium arsenide, you can see here that band gap is nearly a semi metal and compared to silicon. But the point that we need to note here is electron mobility is unusually very high, and therefore this can find use in many of the applications compared to traditional semiconductors. As of now, the most preferred one for semiconductor applications is indium arsenide, because the mobility values are of the order of 16,000, but the graphene mobility seems to even surpass indium arsenide, and this also has a very low lattice constant. The dielectric constant also is very low compared to any of the other semiconducting materials, and therefore this makes it a very good candidate for semiconductor applications as well. So, what are the possible applications? High carrier mobility even at highest electric field, they largely are unaffected by doping, and therefore we can actually go for a ballistic electron transport over less than micron distances, and this can actually lead to applications in room temperature transistors, and energy gap is actually controlled by width of the graphene strip, and therefore we can actually see etching will be difficult consistently, and random edge configuration causes the scattering if we are going to modify the properties of the graphene strip. In terms of other applications, we can look for very high tensile strength, and hydrogen storage also has been noted to be remarkably high for graphenes. Graphene based quantum computation is another thing which is being probed now. I will just take you through few applications before I finish. Generally for this carbon nanotubes and graphene and fullerenes, the spectrum of application is very wide. Carbon nanotubes in particular has already been applied in all these areas. So, I may not be able to run through all the applications, but you can see here it is from electronics to biological applications to magnetic storage, and also in several of our household applications this has found a very useful candidate. For example, when we try to pattern or make graphene sheets, it is easily possible to make a graphene sheet like this. If you pattern your nickel film of this form, we can selectively get a graphene sheet like this using a CVD process, and this can be used for applications. So, so patterning graphene sheets is not difficult, and graphene can also play as a very good metallic contact in transistors, field effect transistors. As you can see from this contour, you can easily make the graphite sheet which is lying here. Graphenes can be made, and then we can put several electrodes for this transistor applications. And as I pointed out to you, depending on the layer thickness, if it is one layer of graphene sheet, then the optical properties are going to be very high, of the order of 98%. But if you are going to make a thicker graphene sheet, then you can easily calibrate using the optical transmittance, it will fall down, and therefore we can have a precise control over that. And it is also reported in OLEDs, if you are going to use carbon nanotubes, then we can actually use this for tuning the colors. For example, if you put single wall nanotubes in buffer layers here, which is in between, if you put buffer layers, holes are actually blocked and recombination takes place in the transport layer, and you can get selectively red. But if you are not going to put carbon nanotube, then the emission will be green. So, this is mainly meant for modulating the charge carrier transport, and therefore the combination of the excitons can be mapped to come either in the transport layer or towards the conducting layers. So, you can actually fine tune the light emission by adding carbon nanotubes in OLEDs. Here also nanotube cathodes can be used for getting preferred colors, and you can also see that the threshold electric field for different materials are given, and carbon nanotube seems to have a very low threshold electric field. Therefore, you can use this for display applications, and already a carbon nanotube cathode has been experimented, which gives very sharp color feature. And in hydrogen storage, carbon nanotubes, carbon materials have been explored. You can see the single wall nanotubes with the lowest purity, giving hydrogen storage capability of 5 to 10%. Those which are currently being used are this graphitic nanofibers, and those are actually having a very high hydrogen storage capacity, but single wall nanotubes also seem to have a appreciable amount of hydrogen storage, and this is still being improvised for practical applications. Lastly, I just want to tell you that this is not only a research effort, but this has become a business venture as of now, and throughout the globe we see many companies have started producing in larger scale, and there is a lot of activity. As you would map here, many companies are from US, which are already producing carbon nanotubes in a preferred way, and there are several activities going on in Europe. We also have isolated activities in Asia, Southeast Asia. We do not have much activity both in South America, Africa, and also in India we do not have any carbon nanotube producing companies per se, but the way the companies have evolved, this gives us a glimpse of what is in store, and therefore many things are going to happen. And just to conclude, as I have already mentioned about graphene, graphene seems to be the basic material for all seasons, and if we can study further, get more insights on to the chemistry or the physics of graphene, then more and more novel properties will generate, and this will have outstanding physical, chemical, electrical, optical and structural properties, and for sure these are going to find more applications in the days to come in field of displays, solar cells and energy storage devices. So to conclude, we have actually seen 3 forms of carbon, namely buckyball, then one dimensional carbon nanotube and also 2 dimensional graphene sheets.